Hi, my name's Adam Alton, and I work at a company called Potato, and I'm going to be talking about building a non-relational backend for Django's object relational mapper. So this talk revolves, this isn't working, this talk revolves primarily around our experience at Potato building a project called Django, which lets you run Django on Google App Engine. So this talk is going to cover our experience of doing that. I'm going to go through some of the highlights, some of the lowlights, and I will also be giving some interesting insights into the inner workings of Django and talking about some of the entertaining things that we've encountered along the way. And as I talk through the things that we had to do to make this work, at some point you're probably going to ask yourself, why on earth would anybody do this? So I'm going to start with the why, and then hopefully when I get onto the how, you're not going to think that I'm insane. So my name's Adam. I'm a big Django fan, and I work at a company called Potato. And at Potato, we build web applications. We're an agency, so we build things for clients, and our biggest client is Google. Now, Google seem to have a habit of sending a lot of users to the things that we build. And this tends to cause a problem. So we need a serving infrastructure that can handle the vast quantities of traffic that Google send at it, and we need a database to go with that that can handle the huge quantities of data and the huge read and write rates that the traffic causes. Fortunately, Google have provided their own hosting infrastructure called Google App Engine, which is their cloud-based app-centric hosting solution. So you package your Python code up in a particular way. There are various restrictions, but that then allows App Engine to clone your application onto as many virtual magic boxes as it deems necessary to serve your traffic. So as you get more traffic, it clones your application onto more machines, and as your traffic dies down, it cuts them down again. To go with that, Google have supplied a database which is specifically designed for handling huge amounts of data and huge amounts of traffic, and that's called the data store. Now, the data store is kind of designed with the idea that whatever you're building is probably Gmail. And so the data store has various limitations, which at first look totally crazy, but if you always think, if I was building Gmail, and therefore any of my database tables could be the email table in Gmail that contains every email from every Gmail account in every country around the world, these limitations then start to make some sense. So what are these limitations? The first limitation is that every query you run must have an index. App Engine simply refuses to go and actually look at the values in all the rows and see whether they match your query. Because if you've got an email table with like 7 trillion emails in it, running a query where it actually has to go and scan the table is just not going to end well. So it won't do table scans. It can only do a query, essentially, where it can jump to a point in your index and then just read data off the disk from that point onwards. So there are no table scans. You can also only have one inequality filter per query. So again, App Engine wants to be able to jump to a point in an index and then just read from that point onwards. So you can say, I want all rows where this column is greater than whatever value. It jumps to that value and reads from that point onwards. But to be able to do that on 2 different columns at the same time with one greater than and one less than something else, it can't do it in that way. So you can only have one inequality per query. And again, it refuses to do things that might take a long time, so it's not going to cross-reference one table with another. It assumes that they are all the email table in Gmail, and that would take ages, so you can't have any join queries. We can do OR queries, but only if they can be split into 2 simple queries that can both be sent off in parallel and the results combined. So, of course, because this database handles huge amounts of traffic, huge amounts of data, your data is sharded across different machines, and it's also replicated across different machines. And that replication happens asynchronously. And that gives us a behavior called eventual consistency, commonly known as, where did my data go? So you can insert new rows into the database. You can then do a query which should return those rows, and they won't come back yet. So it might be that when you inserted them, they got put into a replica over here, but when you did your query, you got connected to a replica over here where those rows aren't copied yet. So that's brilliant fun. That behavior then means that we can't have unique constraints. You can't check and say, does this value already exist? The answer might be no, but that really means probably not. Maybe it's just over there. So we can't have unique constraints except on the primary key. And everything's built with the idea that updating all of the rows could take a very long time. So supposing you want to add a new feature to Gmail, like being able to star an email, you need to add a new column to your email table for is starred. You then have two choices. You can either do this as a single operation, you lock the email table, you add that new column to every row, and then you unlock it. That means you basically lock everybody out of Gmail for a week. So the other option is that you have a database which can cope with some rows having this new column, whilst other rows don't have the new column, and it keeps running in the meantime. So we don't have a schema. In fact, every row can have completely different columns to every other row if you want. Every row is simply a Python dictionary. And you can't, say, do a transaction on an indefinite number of rows. You can't say do a transaction on everything that matches this, because you don't know how many rows that might be. So we can only do transactions if we specify the particular rows we're operating on by the primary key. And because everything is sharded across different machines, each machine has its own set of IDs which it can allocate. So unlike on SQL, the auto IDs are not auto-increment, they're like auto-random. And counting is really slow. So if you imagine you wanted to count how many emails are in Gmail, Gmail would be within its right to slap you and tell you not to do that. So I'm not quite sure why counting on the data store is quite as slow as it is, but it seems to be a kind of good deterrent to stop you doing it. So that's our database. It's very carefully designed and totally insane. So how would that look if we tried to make Django work with it? Well, we can't have joins, so we can't have many-to-many fields, because Django needs to have a through table and join the tables together. And that means we can't have Django's permission system, because permissions rely on the many-to-many field for relationships between users, permissions, and groups. We can't have unique on a field, and we can't have unique together on a combination of fields. Generic foreign key would be fine, but it relies on the content types, and it then does joins on the content types and other tables, so we can't have that either. And we can't have concrete model inheritance. So Django lets you have non-abstract parent models. So for example, you could have a person model, which is a model in itself, with, say, a name field and date of birth field. Then you can have a subclass of that that's a developer model, which has an extra field of favorite programming language. Django then stores the people fields in one table and the extra fields for the developer model in a separate table. And when you query for a developer, it does a join for those two tables to give you all the values. We can't do joins, so we can't have concrete model inheritance. We do have transactions, but they don't work how Django expects them to work. So those are kind of out as well. And pagination, you would think, would be simple, but Django's paginator wants to know how many pages there are. And that's just something that we generally want to avoid. Then the Django admin, well, that would be fine, but it relies on the permission system to control access to it, so we can't have that either. And then there's the migrations, which are kind of a whole other kettle of fish in themselves, which I'll get to later. So this seems like a great idea. Well, that's what we thought anyway. So we built a backend to allow Django to work with this database. So firstly, what is a backend? A backend is the piece of code that allows Django to not know how your database works. So you have your models and your query sets. From your query sets, Django then builds a sort of query object, which is generic Django-ish representation of that query. It then passes it to the backend for whichever database you want to use. And that backend is responsible for then performing whichever particular operations on your database are necessary. This is what we have in Django at the moment, and we've added this. So what's involved in building a backend for Django? Basically, you have to implement a bunch of classes. So there's a database features class, which tells Django what your database can and cannot do. There's a database introspection class, which does things like telling Django which tables do and don't exist. There's a database creation class, mostly for creating and destroying the test database. There's a database schema editor for performing migration operations. And then bringing all of these together, there's a database wrapper class, which is Django's entry point, where it actually talks to your backend. So let's have a quick look at how we had to build those. Database features is basically a bunch of flags. For example, can we return an ID when we insert a new row? Yes, we can. Can we support select related? Well, that relies on join, so no, we can't do that. Do we support transactions? Maybe. This is genuinely a line from our code. Someone set this to false, but quite hopefully thinks that in the future we could set it to true. Then database introspection. This is fairly easy. We just need to tell Django which tables we do and don't have. We know how to do that. That's fine. Database creation. Well, when you create an App Engine application, the data store just kind of exists with it. So we don't really need to do anything here. So we just kind of pretend to Django that we're doing things, and Django doesn't seem to notice. Then we have the database schema editor. Now, we don't have a schema, so again, we just pretend that we've got a schema. And Django doesn't notice that either, so that's fine. And then we have our database wrapper class. So the first thing this does is just points Django at those other classes. And then we have a couple of methods to get a connection to our database. So we don't really have a connection in the traditional sense. The data store has a Python API, and we just call functions on that API. An App Engine then deals with opening RPC connections to whatever part of its magic cloud it's put your data in. So we don't really have a connection. But we pretend to have a connection. We call it a connection. Django thinks it's a connection, and everybody's happy. So it's looking pretty easy, right? But then our connection object has a method on it called cursor, which returns a cursor object. And this has a method on it called execute, which expects to take a string of SQL to execute and a list of parameters to go with it. But we have a Python API that doesn't expect anything like SQL. It just doesn't know what that is. But fortunately, we're in Python. And so a string is just an object with some methods on it. So we pass Django a different object that has some different methods on it. And sometimes it's got some other methods, and then there's sometimes a different object. And there are some other bits of code, and then probably some different objects, and there are some functions to fix some stuff, and then we do a bit more fiddling. And eventually, after some more code, and after 15,000 lines of it, we have something that works. So this has taken us 2,422 commits from 45 different people through 393 pull requests. And the first commit was made almost 3 years ago. So for obvious time reasons, I'm not going to take you through all 15,000 lines of that code. So I've just picked out a few of the interesting bits. So one thing we have to do is normalize where clauses. So Django gives us a kind of where tree, which is a sort of list of lists that represent a where tree. Now, sometimes we get a query that looks like this. It's got an OR in it. And we can't perform this query because we can only do ORs if they can be split into two simple queries that can go off in parallel and then be combined. So we can't do this. But we can do it if we rewrite it into this format. So we have to catch all the cases where Django is giving us one form of where tree and then convert it into one that we can actually perform. If you want to spend the afternoon on Wikipedia, this is called disjunctive normal form. Sometimes we also have to make little tweaks to where clauses. So for example, if you had this on your query set, you might expect that Django would create a where tree that looks like this. But actually, in a traditional SQL database, if you ask for all rows that have a value which is not bananas, the SQL database will only give you rows that have a value which is not bananas. If the row has null for that column, SQL won't return it. So Django actually creates a where tree, which looks like this. So we have to catch these cases, and then we have to convert them back to what we would think of as being the kind of original where tree. Sometimes we have to pretend to have a schema, even though we don't. So this is a piece of Django's documentation for the duration field, and it says that Django stores the duration as a big integer in the database. And this is kind of true if your database coerces it to be an integer. But in actual fact, Django gives you a float. On a SQL database, your column has a type, so that value gets coerced to an integer and it's fine. On a schemaless database, Django gives us a float, we store a float, it comes back as a float, somewhere there's some kind of rounding error that gets introduced, 3.0 becomes 2.999997, then Django passes that to time delta blows up, Django swallows it, and the value comes back as none. So we actually have to look at the model fields that Django's giving us the values for. We have to coerce them to the right type, and then put them into our schemaless database, which doesn't coerce them at all. We found a few interesting Django tests when we were building this. This is one of them. I'm not expecting you to actually read it now, but if, like me, you spent 15 minutes staring at it, you will notice that it has a couple of flaws. In this test, there are two different types of model, and Django is querying for them by primary key to make sure it gets back the right object. But it's actually querying using the wrong primary key. It's querying for a restaurant object using the primary key of a place. But this test has only ever been run on databases with auto-increment IDs. So the IDs of both objects are 1, and you can query for the wrong object, it will still come back again. When you put this on a database with random IDs, it just fails. So we've submitted a pull request to fix that. This is another one of Django's tests. This is the weird bit. It's actually totally unnecessary. So I think that when this test was written, either get required at least one filter argument passing to it, or the person thought that it did. So they've just passed a filter of ID less than 12321. And of course, when your IDs all start at 1 and then become 2 and then 3 and then 4, your IDs are always, in this test, less than 12321. When your IDs are random, this test randomly fails, depending on whether the IDs are greater than or less than 12321. So we've now submitted a pull request to just change it to that, and it works. So that's kind of dealing with Django. So what about trying to make the rest of it work? Well, we can't have unique constraints. But what we can do is have unique primary keys. That's the only thing that can be unique. So we can actually make unique constraints by having a separate table of unique markers where all the primary keys are a concatenation of another table's table name, a column name, and a value that we want to be unique. So we actually implement unique markers by having or implement unique constraints on our model tables by having a separate table that has all the unique markers in it. And we can update these unique markers in transactions when we create or update our model objects. And so by doing that, we have unique constraints back. We can't have many-to-many fields because it relies on joins, but the App Engine data store has a feature called repeated properties, or like list fields. So this is basically a column in which you can put multiple values. So in a single column, we can put a whole list of IDs of another model, and then we can use that to create an equivalent of a many-to-many field, which we call related list field. So we can now have many-to-many relationships between two different tables. That then means we can rebuild the permission system. Using that related list field, we can now have many-to-many relationships between users, permissions, and groups. Then we can have custom user models anyway now. So with that and a custom model backend, we can now build a permission system which is functionally identical to Django's and can easily be plugged in. Now, if you've ever thought about Django's content types, they don't make any sense. So Django has the amazing feature that it will look at your code, and from your models, it can build your database using migrations. Content types are like the opposite of that. They store things in your database, which tells you what your code is. But we know what our code is, and Python can introspect itself. So Python knows what the code is. So when we looked at this and we were trying to figure out how can we remove the issue with needing to do joins on content types, we realized we could just take out the whole database aspect of content types completely. So we've actually just kind of monkey patched that bit out the way. And not only does it work, but it's a lot faster. Now, we can't have concrete model inheritance. We can't store a person table and a separate developer table and then join them together. But we have a schemaless database. So we can actually have concrete model inheritance, but just store everything in one table. This works fine. So you can have a person object and then also store the extra fields for the developer object in the same table. All we then need is an extra column that says, for every person object, is there also a developer instance? And we've got concrete model inheritance back. Now, transactions are just not going to be the same. We have this limitation that we can only have transactions if we operate on particular rows by primary key, but we can still build an interface that looks the same. So we've built our own transaction decorators. We've got the atomic decorator and non-atomic decorator. So we've got an interface that lets you have transactions that look just like they do in Django. And as for the paginator, well, we generally just don't want to count all the rows. But we can easily make a paginator that is the same as Django's, but just doesn't have a page count. So we've built that paginator. It's just a drop-in replacement for Django's paginator, and it works fine. So after all of that, how are we doing? Well, we've got our many-to-many fields back with related list fields. That means we can build our permission system back. We've got our unique constraints. That means that also with the content types, with the database part removed, we've got generic foreign key back. By sticking everything in one table, we've got model inheritance back. We've got our transactions back. We've got paginator back. And because we've got permissions back, we've got the Django admin back. And I'm going to ignore migrations for the moment. So it works. So this is working in Django 1.8 and Django 1.9. You might have heard of a previous project called Django non-rel that was like a fork of Django that tried to do some of this stuff. But this is working on vanilla Django, and the latest versions are fully supported. And not only does it work in theory, but we've actually tested this in production, and I couldn't really estimate actually how many requests we've served, but I reckon we've served at least 1 billion requests last year using this. So it works pretty well. Then we get on to migrations. So the first thing to say is that we still need migrations, even though we have a schemaless database. And that means that you can have a model, you can have your code already deployed, and you've already got objects in your database for this model. You can then add a new model field, and you can deploy that code, and it will just work. And where Django encounters rows that don't have this new column, it just uses the default value from the model field, and it just keeps working. But the problem is that in order to query on these objects and to be able to filter by that field, we need those values to be stored in our index. So we actually need to go and resave the objects in order that they go into the index. So we do still need migrations. But we don't have SSH. We can't just like log into our server and go and run some commands on our server. There is no server. There's just like the magic cloud. We do have a connection to that magic cloud, and we can run operations on our database from our laptop. But if your migration is like a few million rows and it's going to take 6 hours, and you want to take your laptop home, it doesn't really work to have this connection open running database operations from your laptop. But App Engine has tasks, so we can send off tasks to go and map over our data and resave things in the background. And what we really want to be able to do is to be able to run migrations from the Django admin. So we're currently working on this. We're working on implementing some form of migrations. And our plan is to be able to, you just go into the Django admin, it can list your migrations, it can show you which ones are run and which ones aren't, and you can just run them straight from there. But first we have a little problem. Django's migration module has a migration recorder, which has a sort of nested hidden model in it, which records which migrations are applied or not applied. And that's where the problem comes in. Django has a concept of migrations being applied or not applied. It doesn't have a concept of migrations being in progress. So this is currently causing us difficulties. And ironically, this is the only model in Django that you can't modify because you can't run migrations on the migration recorder. So that's a fun little thing. We're still working on that, but we do hope to not only make migrations work, but also make them work in the Django admin and possibly even contribute that back to Django. So that's basically it. Just a few closing thoughts. What can Django do with all of this, other than obviously going back in time using the Hermione's watch and putting that field to be nullable and not giving us floats? I'd love Django to embrace this. We've shown that this is possible. We can do this on vanilla Django. It doesn't really require any modifications to Django. It actually kind of helps to improve things by fixing some tests. What can you do? You can do those things because Django is not a person. It's just us. You can try this out. I'm going to be here for the rest of the conference. I'll be here for at least the first day of sprints. Or if you find anyone with like a potato stuck to them or on their t-shirt, you can go and hassle them. Download the code on GitHub. It's on the next page. Feel free to go and try it out. When it doesn't work, come and grab me. Give it a go. And if you're really daring, you could try building your own backend. There are other non-relational databases out there. It would be really good to have some friends in the Let's Build Crazy Backends community. So finally, this talk wouldn't be complete without saying thank you to people. There have been 45 contributors to this project on GitHub. One of them in particular needs mentioning because without him, this wouldn't have started. My friend Luke Benstead, who works at Potato, he came up with crazy ideas like let's put all the fields for multiple models in one table. And without him, this project really wouldn't exist. And on that note, that's it. Thank you very much.
Thank you, Adam, for tackling this daring subject of non-relational ORMs.
I should say we've got potatoes. If anyone would like a potato, I think people who ask questions get a potato. They're not edible.
All right. Mad props for you getting to you and 44 other people to get this working because it's there's dragons in there. I'm fully aware. The question I've got is this has obviously started like 2013, I think you said.
Yeah, and we started as Luke Benstead's kind of personal project.
Right.
So it was kind of slow for the beginning. So it's possibly slightly misleading to say this took like 3 years to build.
Right. Okay. Have you had a chance to look at the stuff that was added as a result in 1.8 as a result of the Summer of Code? Because you're attacking it at the level of the database layer and trying to make something that is SQL-like but not SQL. But if you pull back a layer and do it at the level of the duck, like make duck tucking the models, you can get things like admin and permissions and whatnot transparently without having to go through like reinterpreting queries. Did you have a chance to look at that, or have you had a look at any of that?
No.
Right.
So I'm not entirely sure what you mean as to which layer to go into.
Yeah,
but maybe we should discuss that afterwards.
Yeah, sure.
Cool. Have a potato.
So the first thing is duration field is my fault. However, some lovely person 3 weeks ago has fixed it, so you'll now get an integer on the next version of Django.
Oh, cool.
I do actually have a question there, because related to that in the work I was doing there, I'm kind of curious as to how you worked around the problem of things, aside from the fact it gave you the wrong value, but the problem of dealing with database level conversions for different things. Because there's a feature, sort of privatist feature that was introduced around the same time as duration field came along that is supposed to help custom database backends hook in, they're called converter functions, to allow you to change the data type from, so it's what we use in duration field for Postgres to do nothing with the time delta and just pass it off to the database because Postgres understands, and if it's not some crazy database, turn it into what was supposed to be an integer. So is that a feature that you're using, or are you doing it yourself further down the tree, or how do you deal with data type conversions, basically?
To be honest, with 15,000 lines of code, I can't remember. I think we're using the way that Django expects us to do it. I don't think it's like a dirty hacking things in the wrong place. I think we're doing things in the way Django expects.
That would be good to know if that actually works, because I didn't know whether it did or not.
Okay, I'll try and find out for you.
Hi. I think, just making sure that I didn't miss something at the beginning, you said that Google App Engine doesn't support joins, and you talked about how you solved the many-to-many problem, but how did you solve the kind of arbitrary join across models problem, and if so, how?
No, so we can't do anything that looks like a join, but essentially we can have model structures that have many-to-many relationships in them. Does that answer your question or not?
So, the real question is like reverse lookups. How would you make that work?
Okay, so with App Engine's like repeated property field, it indexes all of those values individually. So if you have like a model that has a related IDs, list of IDs on it, that points to like model B, if you've got an instance of model B, you can actually query for the model A's that have this ID anywhere in their list of IDs, if that makes sense. So you can query back on that multiple value field, and therefore you can do the lookups both ways. You can say, I've got a list of IDs, give me all model B's that are in that list. Or you can have an instance of model B and say, give me all model A's that have my ID in their list. So you can do it both ways, yeah. Last potato left.
Thanks, Adam. The way you fixed, or however, the generic foreign keys, is there anything we could get into Django as in, I personally think there are a couple of fundamental problems with generic foreign keys. They are the way they are implemented. Is there anything we can take out of Django and get into Django to make them more sane?
I think there probably is, yes. I'm trying to remember whether it's compatible. Like if you've got a project already deployed, and therefore all your content types have got IDs in the database, as to whether our system would cope with that. I forget what it uses as its IDs. So you might have a problem of like deploying that to a new project. But essentially, yes, I think Django can probably take what we've done, or we can send it to Django. I think there's something to be learned there, and I think I don't think there's any reason why we need to have content type things stored in the database. So yeah, I think we could take that and port it back to Django.
Thanks. Comment, I'm not going to say here, talk to me later regarding the recorder.
I didn't hear that, but it was a comment, so it's fine.
Regarding the migration recorder later.
Okay, have a potato.
First, thank you for the 15,000 code lines. Second thing, I need to understand more why I need migrations. From what I understand from NoSQL engines, that adding one field, you don't need migrations. And for indexing, you need to define the index fields for something you are sure there is a data there, like IDs, name. Why you need migrations for NoSQL? Like for MongoDB, there is no need for migrations.
So you're talking about the example where you've added a new field to your model and the default value is none, right? So you would think you don't need to go and resave anything to get that to go into the index because it's none. But the way the data store indexes work is there's a difference between this has a value of none and this doesn't exist. So in order to query for like objects where this value is none, you actually need to have set a value of none in that field. So you kind of think, oh great, let's just, we can run our queries, and because the value isn't there, it will give us the objects back, but it actually doesn't. So we do need to go and resave things to save none in the index.
About the field I've added into the model, it becomes the index, right?
Once you've resaved it, yeah. Yeah.
Okay.
All right, last question.
Okay.
Hello. Quick question. When Django will leave the beta version?
Sorry, say that again.
When Django will leave the beta version?
When will Django leave beta?
Oh, I see. When Django leave beta? It will leave beta once we've got the migrations done, essentially. There's a little underlying thing to do with the way App Engine stores these list fields, which we want to be able to change, because they've changed some like detail of the implementation. We want to be able to fix our existing projects using migrations so that we can then change our behavior of how we deal with list fields. So once those two things are done, it will come out of beta.
All right, all questions now. Thank you very much.
Thank you.